All right, team, this is the Met Corrections homework from the Mod 2 notebook. On this version of the Mod 2 notebook, this starts on page 154. All right, so we're going to be in chapter 1.1 of the TC, meteorological techniques. I'm going to have a couple of things with me to do this homework. I'm going to have some blank DA form 4200s. I'll have a four-function calculator, some notes that I have from class, as well as some registration theory notes that we have, right? So we have this handout that has a ROF that we're not going to need because we use this for concurrent MET. I have my registration theory, GFT setting notes right here, as well as how to apply a GFT setting and the registration theory temperature and density conversions for my DA form 4200. So let's go ahead and jump right into it. So, situation: you are the FDO for Alpha Battery, 1st to the 30th, 6 Paladins. After occupying your firing position, you determine that you are meeting the 5 requirements for accurate predicted fire, but are not adequately compensating for all non-standard conditions. In order to achieve accurate first round fire for effect, you determine the use of a GFT setting is necessary. Okay, so requirement 1. Your battery commander asked you, if you are meeting your 5 requirements for accurate fire, what technique can you use to determine firing corrections to compensate for non-standard conditions? Okay, so this sounds like something that we'll probably find inside of the TC, a general knowledge question. So it's probably here in chapter 1.1, meteorological corrections. But let's check here on page 11 dash. Let's see here. Yep. So 11-53. Okay. So if we are meeting our 5 requirements, right? So if the battery is meeting the 5 requirements for accurate fire, there is still a need to improve data for meeting the GFT, and I use a MET plus VE technique. Okay, so the answer to requirement 1 is a MET plus VE technique. All right. Number 2, a registration has been conducted, and you are required to establish 6,400 mil firing capability. What technique can be used to establish an accurate firing solution in all directions? Okay, so in all directions, we're talking about 6,400 mils. I need to be able to shoot in any particular direction. We conducted a registration in one of the octants, and so that sounds like we're going to need to turn back a couple of pages over to 11-52, and yep, sure enough, here it is, the 8-direction MET technique. Eight-direction MET technique. Okay. So an explanation of what this is. So really, there are 2 requirements that we have to have. So the first is that we get a solution of a concurrent MET technique to determine the pause VE correction, right? So basically, we run a registration in one of the 8 directions. And then after we do that, we use the MET plus VE technique and the pause constants from whatever octant to determine our GFT setting for those additional octants. So the way that this works, and I drew this out here. So the way that this works is this right here in the center. This is our firing battery. This is our registering howitzer, right? So we registered on this particular known point. This could be a known point. It could be, I don't know, a spot on the ground. It could be a bush. It could be a tree, whatever it is that we identified. We conducted a registration on this point, and we extracted a GFT setting, okay? So the GFT setting, we're calling it GFT1 because it's going to be in octant 1. This GFT setting that we calculated to this known point right here is only good for 400 mils left and right of the direction of fire, or 400 mils left and right of the gun target line that we registered with, right? And that GFT setting, those 400 mils left and right only go out to 10,000 meters. Beyond 10,000 meters, it no longer has the 400 mils left and right. It turns into like a corridor. Turns into a corridor that goes pretty much into infinity, but the corridor diameter is 8,000 meters, or 4,000 meters left and right of that gun target line that we shot the registration with, okay? So basically, if a target plots anywhere inside of this octant, right here, I can use my GFT setting I calculated right here for this registration. But it's saying, what if a target plots outside of that octant? What if a target plots over here, right? It is outside of the GFT transfer limits that we said 400 mils left and right, right? So what happens if a target plots out here? I can't use the GFT setting that I calculated here. So what I have to do is I'm going to run a concurrent MET, take the pause constants that I determined here at this known point, extract those pause constants, and then conduct a MET plus VE technique apply the pause constants, and get a new GFT setting for octant 2. So that way, if a target plots anywhere inside of this octant, I can use the GFT setting I use for octant 2. And I do that in all 8 directions, right? Using a MET plus VE technique. Preferably a MET to MET check gauge point, right? So if we're shooting like charge 1, the MET to MET check gauge point for charge 1, give me a second, let me grab my GFT. Grab my low angle GFT here. All right, the MET to MET check gauge point for charge 1, this particular case, is, it looks to be right here at about range 5050 or 5060, right? So the red equilateral triangles are MET check gauge points. So what I would do is I would run a MET plus VE technique to that particular gauge point at chart range 5060, right? It's just an arbitrary spot that I picked. It doesn't have to be a physical object on the ground. Then I'll run a MET plus VE technique on a DA form 4200 there, apply the pause that I calculated here, applied over here, and then that is my GFT setting. And I do that in all 8 directions, right? Now that way I have 8 different GFT settings, and now wherever a target plots, I can use the appropriate GFT setting, okay? So one of the things I will say about this though, and we're about to refer to this here in a second, is because of this corridor that happens at 10,000 meters, right? It goes from being 400 mils left and right of the gun target line we registered with to having these corridors, right? Between these octants, I have this dead space that my GFT settings cannot be used, right? So if a target plots here, what do I do? And we're about to discuss that here in one of the requirements on the down here, okay? So number 3, can the position constants from the registration be used to fire on targets that require a different charge than the one you registered with? So basically, if we registered with charge 1 and we have a target that we want to execute with charge 2, can we transfer the position constants? Well, let's check the TC and see what they say. So we're going to refer to page 11-4 in our TC. Yep. So 11-4 is where we have the paragraphs on position constants, or pause is what we call them, right? So if I see, let's see here, yep. So the position VE is a constant for projectiles within the registering projectile family. Okay, so projectile family sounds like I can transfer pause. And then 11-10 says part of the position VE and position deflection correction are charge independent, specifically errors in the chart, the firing chart and survey. So the answer is yes, because pause is charge independent. Independent, there we go. Charge independent. That doesn't mean that we can just transfer our GFT settings between charges. That's not what it's saying. It's saying once we run a concurrent MET technique and we isolate pause, I can use that pause on different charges as long as I'm using the same projectile family. Because that pause VE and the pause deflection are really just errors in survey and firing charts, manual firing charts, okay? All right, so number 4, after determining a GFT setting, you process a fire mission and you notice that the target plots outside of the deflection transfer limits, which is left and right 400 mils, the direction of fire from registration, which we already discussed. If your chart range was less than 10,000 meters, what subsequent MET application should you use to achieve accurate first round fire for effect? So this first part is saying, if I have a target, if this is the point that we registered at, we'll just call this known point 1. If we registered at known point 1 and a target plots outside of my deflection transfer limits, right? What MET technique do I use to be able to prosecute that target? We referenced it up here. It's the 8 direction MET technique, right? I would just use the GFT setting I calculated for octant 2, all right? So first part would be 8 direction MET, okay? So there's a second half to this question. It says, conversely, what subsequent MET application should you use if your chart range was greater than 10,000 meters? So really what this question is saying is that if for some reason I have a target that plotted like right here and it was greater than 10,000 meters, somewhere out here, right, in this dead space, what MET technique do I use, right? So if we wanted to refer to it, we would come here in our TC towards the back of this chapter. It briefly mentions it at the back of chapter 1.1. See, here we go. It's right here on page 11-52. It's called MET to a target. So basically what it's saying is that if I have a target that plots outside of any of my octants and any of my GFT settings, I have to do a MET plus VE technique to that specific target. That means I have to run a DA form 4200 to that specific target to get my GFT setting that I will use one time and one time only. Obviously, this is very time intensive. So we really only do this for super, super important targets, what we call that are on the HPTL or the high payoff target list. Okay. So the answer to this second part right here is, what do we say? MET to target. MET to target, okay? Now what I always recommend for my FDOs is that you basically copy an octant overlay like this on a piece of acetate. You copy it like this on a piece of acetate, and then that way whenever you occupy a new firing position and you register, you can just put this on the firing unit location and you can turn it in whatever direction you need to, right, to establish your octants based off of the azimuth of fire or based off of where you registered your howitzer. All right. Okay, so we finished our general knowledge questions, so let's go ahead and turn over and execute requirement number 2. Okay, so let's start requirement number 2. Given the following data, complete a MET plus VE technique using DA form 4200. So this is our known data. We're always going to be given a little bit of known data anytime that we're executing one of these for homework or for the exam, right? But obviously in real life, we would be the ones determining this known data, right? So chart range is 8330 MET check gauge point. Direction of fire is 0395, and the charge is 2 Lima, right? So let's talk the direction of fire first. That direction of fire was probably determined based off the tactical situation. 0395, maybe that's the direction that most of the targets are that we're going to prosecute for a given operation, right? We see we're firing charge 2, and the chart range that we're going to use is 8330, which happens to be a MET check gauge point. So if you refer to your low angle GFT for charge 2, you'll see that this MET check gauge point is a red equilateral triangle here at range 8330, right? It looks to be a little bit less than that, but we always go up because that's going to be the range crossover point where our projectile passes through an additional line of MET data. So anytime that we're doing a MET plus VE, if we can pick a range that is a MET check gauge point, that's the ideal place to do it, okay? Our particular case, we have range 8330. For the executive officer, so registered fuse is Mike 582. It could be 582 or Mike 767. Doesn't really matter. They function pretty much the same way. Projectile weight 5 square. Prop temp is 32 degrees Fahrenheit. Oh, it must be cold. We're probably training in the winter or something. From the map and firing chart, alpha battery altitude. So our altitude is 326 meters. Latitude is 66 degrees north. And this is our MET message from the MET station. And then from the alpha battery muzzle velocity logbook, which every good FDC should have, I see that we have MVVs for number 3, Shell HE Lot Alpha Lima, charge 2, MVV negative 38 point meters per second. So we already have an MVV for this propellant lot with that propellant charge. Cool. So we're going to perform a MET plus VE given this data. So MET plus VE, there's not a step action drill for this in the TC. You can use the MET check gauge point step action drill if you wanted to. Or you could refer to your Mod 2 notebook. But the big takeaway about a MET plus VE technique, there's really 2 big things. Number 1, I can just make a note here. So number 1, for MET plus VE, VI will always equal 0. Okay, VI is always going to equal 0 for a MET plus VE. And number 2 is that for a MET plus VE, looks like here, because we don't have any pause constants, pause will also equal 0. Okay, and we're going to keep that in mind when we fill out our DA form 4200. This will go significantly faster than the concurrent MET that we did in the previous homework. So we're just going to jump right into it. So the first things first, we're going to fill out all of the things that we already know are known data. If you don't already have it, go ahead and get your Christmas tree in front of you. Let me go ahead and grab mine here. So when I say Christmas tree, this is what I'm talking about. So we're just going to get this. I'm going to have this off to the side. I'm going to be referencing it to see where we get certain things from. But as a review, everything in red is stuff that we already know. Everything in blue is stuff that we get from MET messages. And everything in green is stuff we get from the TFT. Right? So that's going to be off to the side. I'll be referencing that as we go. So let's start from the top. So let's see here. So what charge are we going to be shooting? No data says charge to Lima. I don't have an adjusted quadrant elevation because I'm shooting a MET plus V, or I'm calculating a MET plus VE. Chart range is 8330. We also pop that down here, 8330. Got my latitude, 66 degrees north. I express that to the nearest 10, which would be 70 degrees north. Okay. Let's see, what else do we have? Let's come back up here. So my direction of fire. Direction of fire is 0395. Put that in parentheses here. Then express that to the nearest 100, which would be 0400. Okay. Again, the method that we're using right now is just called like the fill it out method. It's just find what you can when you can. Okay. So let's keep going. Let's keep working up here. So the altitude of the battery, where do we have that? Alpha battery altitude is 326. So we're going to record 326. And we express that to the nearest 10, so that would be 330. All right, don't know the MDP altitude yet. We got to look at the MET message here in a minute. So let's keep going through here. So the altitude of the target. What did we say about a MET plus VE? VI is going to be 0. So there is no altitude of the target. There is no height of burst above target. There is no altitude of burst. The altitude of battery, we're not really concerned with that either, right? Because the main thing that we're taking away from this is that the height of target above gun, or the VI, is going to be 0. And you can see once we get into table Bravo, but if I have a VI of 0, I know my complementary range is going to be 0, which means my chart range of 8330 is going to express to my entry range of 8300. Okay. All right, so let's see here. What else do we have? So let's fill out our equation right here. So we know that for a MET plus VE, all of our pause is going to be 0. So my pause deflection correction is going to be 0, okay? I know I'm going to have to add my MET deflection correction. So let's go ahead and record this equation here. MET deflection correction. I don't know what it is yet, but I'm going to get it here in a minute. And I know that both of those are going to give me my total deflection correction, which is the goal of a MET plus VE. The goal of a MET plus VE is to get a new total correction, okay? All right, so let's see. What else do we already know? Let's keep going down here. So projectile square weight. What is our projectile square weight? Projectile square weight is 5 square. And I already know that my standard square weight is what? 4 square. Let's just go and fill it out right now. That means that I have an increase in 1 square, okay? As we keep coming down, I know that I'm going to have to set up my VE equation, right? So my VE equation is going to be pause VE plus my MVV plus my delta MV weapon. Let me record that. Plus delta MV weapon. And all of that is going to equal my total velocity error, right? So pause VE, because for MET plus VE, pause is always going to be 0. Pause VE is 0. Plus my MVV of negative 3.8 meters per second, plus delta MV weapon of 0 equals a velocity error. So we can go ahead and solve that right now, can't we? So we have, and the reason why the delta MV weapon is 0, even though we're shooting charge 2, is because we said we're shooting paladins for this problem, right? We're shooting paladins. Okay, so negative 3.8, all that. Yep, let's just solve it. So that would be negative 3.8. Then we're just going to pop that right here. Negative 3.8. Since we're here, what's my prop temp? Prop temp is positive 32 degrees Fahrenheit. All right, a little chilly. Okay, so for a pause VE, I've already got this one. I've already got my block cut in half. I know this is going to be a delta. This is going to be India because it always is. For a pause VE, I'm going to cross out the total range correction up here. Okay, and I'm going to keep working my way down. All right, let's see. For MET fuse correction, if it's not recorded, I would record fuse setting and adjusted elevation, right? We have to get our adjusted elevation to get our fuse setting down here in our lazy Z, right? But we do know a couple other things, right? This right here, our should hit range. Let me refer to my GFT notes, GFT setting notes. So in my lazy Z, this is my should hit range. Should hit range is the same thing as my chart range. right? So my chart range I see on my known data is 8330. That's the range to my met check gauge point. So this is going to read 8330. Okay, so basically I need to find my total range correction is the first thing I need to find. As soon as I find my total range correction, I can, like domino effect, find everything else, okay? All right, so I have this, let's see here. So for Met plus VE, that really shouldn't be lined through. It's just the one that I printed, but we'll just go ahead and mark it through. Met plus VE should have this one lined out, not this one, but we'll make do. It'll be all right. I know that my fuse correction on here, this is actually referring to my pause fuse correction, right? We know that pause for Met plus VE is going to be 0 because I didn't run a concurrent Met. I don't have any pause to actually transfer into this, right? So target number is going to be Met check gauge point. All right, we said that our battery was alpha battery. I can also see that on my GFT, right? GFT setting. Well, it says number 3, but I know that I'm an alpha battery. Normally, unit, this would be alpha, but this is, I'm sorry, this is my muzzle velocity correction. What am I talking about? I know that I'm shooting alpha battery, okay? So date time group. So while as of the time that I'm recording this, the date time group. So we do the date. So it's 1/4, that's the day. The time, I always express time in Zulu, right? Zulu time is 2:253 Zulu, APR 23. All right, so I got my date time group. Okay, so that's all of the data that I have from my known data sheet here, right? I've got everything that I could possibly pull from my known data sheet. So I can just start filling out my, my DFM 4200. Immediately after getting my known data, what I like to do is I like to go to my MET. So I like to get all of the stuff from my MET message. So starting up here, my MET message, what type of MET message is it? It is a computer MET message. Computer MET, octant is going to be 1. So that's what octant of the globe that we're in. Area unit is 661.109 or 66.110.9. That's my latitude and longitude. Okay. Next, I have my date. So date for this, let's see here, is 05. The time is 0650, but that would actually be 0630 Zulus because that's 06.50. Okay. Next, I have the altitude of my MDP. Remember, this in the MET message is in tens of meters. Okay, in the MET message is tens of meters, but here I need it to the nearest meter, which would be what? 230. All right, and next I have my pressure of the MDP. Pressure of MDP is 921. All right. And if I wanted to check the validity of my MET message, first thing I'd look for is my the pressure of my MDP, the same my pressure of my line 0. Yes, it is. I can also look for a couple other things. I can refer to, in my TC, figure 11-6 in my TC for MET message validation procedures. And I can check the wind direction to make sure that I don't have anything over 1,000 mils. Yep, it looks good. I can look at my wind speed, make sure I don't have anything over 10 knots. Yep, looks good. I can check my air temperature, make sure I don't have a change of 20 degrees or more. Let's see here, a total of 20 degrees. Yep, looks good. And then I have, if I have any pressure increases. Nope, no pressure increases here. So that message looks like it is definitely valid. Okay, so after I have that, we need to determine, let's see, we got our altitude of the MDP, so let's go ahead and pull it over here. Altitude of MDP is 230. While we're here, let's go ahead and find whether or not the battery is above or below the MDP. So the battery altitude is 330. Is that above or below the MDP altitude of 230? It's above, so we're going to circle above. Okay, and now what we're going to do is we're going to do this number minus this number. So 330 minus 230 is going to give us a delta H of positive 100. So that means that the battery is 100 meters above the meteorological datum plane, okay? All right, so after we have that, we need to find our line number. How do we determine our line number? For a MET plus VE technique, we use table Bravo because we don't have an adjusted quadrant elevation. We only use table Alpha to determine our line number is if we shot a registration and are running a concurrent MET technique. So for MET plus VE, we have to use table Bravo because we don't have an adjusted quadrant elevation. So I'm going to refer to my TC, or correction, my TFT for the Alfa Romeo 2. I'm in table Bravo, charge 2 Lima, here on page 152. So let's see here. My chart range is 8330. Is that a listed value? No, it's not, but it is close to 8300, right? I said my VI is always 0 for MET plus VE. VI is 0, so I bring them together. What's my complementary range? Complementary range is 0, which we already said. Drop the ball down the stairs, let it roll down the stairs. I'm using MET line number 03. MET line number 03. Okay, so now that I know that I'm using MET line number 03, I'm going to highlight MET line number 03 on my MET message, so I don't accidentally pull data from a different line. Okay, so that's the MET line that I'm using. All right, so let's start extracting data. So wind direction, remembering that wind direction here is always in tens of mils. So that's 480 would be 4800, right? Wind speed, this is always in knots. So wind speed is 25 knots. Air temperature. So remember, this is in Kelvin and this is in millibars, and I need to transfer, or I need to convert this to my air temperature, my ballistic air temperature, my ballistic air density. And to do that, I use, let's find it. I use my temperature and density conversion formula from my notes. If you don't have this in your notes, go ahead and screenshot or pause the video here. Go ahead and record this conversion equation, okay? I'm gonna flip over my DA form 4200 and do it back here. A lot of people do it here, but I don't think I have enough space. I like to have lots of space to do my calculations. Okay, so first thing I need is my air temperature from the computer MET message in degrees Kelvin. So we said that was 239.7. 239.7 divided by standard air temperature from TC 3-0991, page 11-13, figure 11-8 in degrees Kelvin. So let's go ahead and extract our TC, turn it to page 11-13, and again, figure 11-8, and I'm trying to find the standard air temp for degrees Kelvin. So we said this was for line 3, so I can see here for line 3, standard air temperature is 283.3. Okay? I'm going to take that value, I'm going to multiply that times 100. Right, that's the step where I'm at right here. So let's see here. 239.7 divided by 283.3 equals that number times 100, which is going to give me 84.60. And I see I expressed this to the nearest tenths, so it'd be 84.6. And that is the answer I'm going to use for my 4200 air temp. Cool, now that I got that, we got to get down here to air density. So air pressure from computer MET message in millibars. What is it? It is 793 millibars divided by, well, yeah, I'm going to multiply it times this disgusting clown number times 0.34836764. All right, and then I divide that by the air temperature from the computer MET message in Kelvin, which we said was 239.7. Okay, and then that's going to give us a number. So 793 times 0.34836764. I can't even fit in my calculator because it's so ridiculous. Gives us that number right there, divided by 239.7. Gives us 1.1525052. I see I expressed this to the thousandths. Let me put that in one more time. So 793 times 0.34836764. is that number divided by 239.7. Yep, gives me 1.1525. All right, so now I'm going to take this. Okay, so I'm going to bring this value down here, 1.1525. I'm going to divide that by standard air density from page 11-13, figure 11-8. Okay, so right here, standard air density for line 3 is 1.1392. Okay, so I have this, and then I'm going to multiply that value times 100. 1.1525 divided by 1.1392 gives me that. I multiply that times 100. That's going to be 101 point, let's see here. I need to express this to the tens, so that's going to be 101.2. Okay, now I take that number, so 101.2, and then I multiply times the density weighting factor from page 11-13, figure 11-9. Just here, so density weighting factor for line 0 through 03 is 1. So that means that 101.2 is the answer that I need for my 4200 density. All right, sweet. So I've completed my conversions for MET, from computer met to ballistic met. So let's plug these numbers in. So I have my air temperature, we said was 84.6. That's 84.6%. Air density is 101.2%. Since we're over here, let's go ahead and find our delta H corrections. So where do I get my delta H corrections from? I could look on my Christmas tree and I see that I get these from table delta. Delta H goes to delta. Pretty nifty there. Okay, so extract our TFT. Let's go to table delta, which is here on page 159. Okay, delta, page 159. So I see that I enter with the delta H. So the delta H is right here. It's 100, and the battery is above the MDP. So 100 and 0. Okay, so I come in here, so I see my values are 0.2 and 1.0. So that is 0.2 and 1.0. But I need to determine what my sign is. So if the battery is above the MDP, use the sign before the number. Is it above? Yes, it is. So the numbers are going to be negative. So that is negative 0.2 and negative 1.0. Okay. Okay, so now that we have that, we're going to go ahead and just apply this to our air temps and our air density. So that's air 84.6 minus 0.2 gives us 84.4. And as soon as I solve this, what I'm going to do is I'm going to pop it down here. And the reason I do this is because later on, I don't want to accidentally extract this number. I want to extract this number, the corrected value, okay? So my air temperature corrected value is going to pop down here as 84.4, all right? Now I need this one, air density. So 101.2 minus 1.0 gives me 100.2. Pop that down here, so my air density is 100.2. Okay, sweet. So now that I've got that, I've got pretty much everything done up here, except I need to take that direction of the wind and pop it down here. Right, I took 4800, popped it down here. Take that wind speed 25 and pop it down here. All right. Now, after I have that, I'm pretty much done with the top fourth of my 4200. Now I need to go ahead and start my wind components and my deflection. So I have my direction of wind, which is 4800, minus my direction of fire to get my chart direction of wind. So that's 4800 minus 400 gives me 4400 as my chart direction of wind. Okay, so what table do I enter with chart direction of wind? Chart direction of wind starts with a C, that's table Charlie. I'm gonna move this off to the side here. So table Charlie. All right, so chart direction of wind is 4400. Let's enter right here. I see 4400. The two values I extract for my crosswind is left 0.92. For my tailwind, it is a tailwind of 0.38. Okay, and that's all I need from table Charlie. All I need from table Charlie. All right, so now let's go ahead and multiply across. So we have 25 multiplied times 0.92. Gives us 2,3, which then we express to the nearest not, which is just 2,3. And it keeps the same sign as the correction. So that's left 2,3. I got to get something from over here in just a second. We're going to come back to that, okay? Let's go ahead and do this. So I have wind speed of 2.5 multiplied times 0.38. Gives me 9.5. 9.5 is going to express to the nearest not, which is 10. And it keeps the same sign, which is a tailwind. Tailwind of 10 knots. Okay? So now what do I do with that? That is now my range wind value. This is now a known value. I take this and I bring it down here. A tailwind of 10 knots. Okay? If I wanted to, I could just say, all right, if this is a tailwind of 10 and the standard value is 0, I have a tailwind of 10. All right? For us, this is always going to be the same. Okay, so now I have that. Let's go ahead and find our unit correction for our crosswind. We're going to find that in table Fox. That's what my Christmas tree tells me to go to, is table Fox. And my entry range is 8300. So charge 2, range 8300. And I see my value for azimuth correction for crosswind of 1 knot is column 9. So at 8300, that is 0.44. Okay, so now that I have that, I can go ahead and multiply 23 times 0.44. That gives me 10.12, which expresses to left 10.1. That's because it keeps the same sign. This has the same sign all the way throughout, right? Okay, So now that we have that, let's go ahead, since we're in table Fox, let's just find our drift correction. Drift right here at range 8300, so entry range 8300 is going to be left 9.6. Okay, now I have my rotation correction. Let's just go ahead and find our Met deflection correction while we're here. So where do I find my rotation correction? My rotation correction is going to be table India, right? Because table Hotel was my rotation for range. Table India is my rotation for azimuth. So we see that I need to enter with what my latitude is. What's my latitude? 70 degrees north. So 70 degrees north latitude. If it isn't already done, I'm going to highlight 70 and north, 70 and south. I'm going to highlight that rock star line so I don't accidentally extract high angle data because we're shooting low angle. Okay, so where are we? Here we are. All right. So my entry range, 8300, not a listed value, so I'm going to go to 8000. And then let's see here, my direction of fire. So my azimuth to target, 0395, not a listed value, but it is close to 0400. So I come in here and I see that my value is 1.7. So I'm just going to record 1.7 real quick. But is it a left or a right? When entering from the top, use the sign before the number. So it is a left 1.7. All right, so now let's add all of these up to get our overall Met deflection correction. It looks like they're all lefts, so I'm just going to treat them all as positive numbers. So 1.7 plus 9.6 plus 10.1 gives me 21.4, specifically left 21.4, which then expresses to left 2.1. And that is my Met deflection correction. So I'm going to take that, I'm going to pop that over here, left 2.1 to give me my total deflection correction of left 2.1 because I said my deflection pause was 0 and my Met deflection correction was left 2.1, so my total deflection correction is left 2.1. That is the first piece of total corrections that I'm looking for in this DA form 4200. All right, I've just got 2 more. So let's move on to the Met range correction. All right, so my Met range corrections. See, I've got all my known values except for my rotation of the Earth. Okay, so where do I get this known value? I get this in Hotel. So if you believe that the Earth is round, we go to table Hotel to find our range correction to compensate for the rotation of the Earth. If it isn't already done so, I'm going to go ahead and highlight the rock star line to make sure I don't accidentally extract high angle data. And then I'm going to highlight this table down here because table Hotel is a very, very tricky table. And if I forget to extract this number as well, I'm not going to get the right value. Okay. So let's see here. So my range is 8300, not a listed value, but it is close to 8000. Azimuth to target, 0400. Bring them together and I see that it is 1.1. Record 1.1, but what sign does it take? Let's see here. Look down at the notes. When entering from the top, use the sign before the number. I entered from the top, so that is a negative 1.1. Don't forget about the secret table down here, right? I need to find what my standard value is right here. So based off of my latitude of 70 degrees, I see that it is 0.34. Okay, we're eventually going to do that math, and we're going to put that value somewhere over here, okay? All right, so now that we have that, let's do our variations from standard. So air temp is 84.4. If standard is 0, I have a decrease from standard, right? Decrease, so that's 100 minus 84.4. Gives me 15.6, so a decrease of 15.6. Air density 100.2. Standard is 100, so I have an increase of 0.2. All right, and then we already did the square weight earlier, and we already did the rotation of the Earth. So now I need to find my unit corrections. I find these unit corrections in table Fox. That's what my Christmas tree says. It says to go to table Fox. Okay, so let's see here. So I'm at entry range 8300. Entry range 8300, charge 2. Let's see here. I'm not going to find them there. I'm going to be over here. Okay, so page 165 of the Alfa Romeo 2, so 8300. All right, so I got my first unit correction. It needs to be for range wind. It was on the other side. Dang it. Wait. Whoop. What am I looking at here? What am I looking at here? Where is it? Oh, range wind. Yep, sorry. Crosswind is on the previous pages. So column 1, 2 and column 1, 3. So I have a tailwind. So tail, actually, let me get a straight edge real quick so you can see which ones I'm looking at. That's probably not going to do very well. Especially when extracting data from table Fox and table Juliet, it's a good practice to use a straight edge to make sure you don't accidentally extract from the wrong column. Okay, so here we go, 8300. So entry range 8300. I have a tailwind. So let's see here, tailwind, I come down, I see that the value is negative 10.1. All right, this value is negative. This value is negative. That means that this value is going to be negative, so I'm going to cross through the plus column, okay? So next I have air temperature. I have a decrease. Air temp, decrease. That means positive 17.8, which means I'm going to cross out the minus column, okay? Next I have air density. Air density has an increase, so that's column 17. Air density is 20.9, positive 20.9. Okay, I'm going to cross through the minus column. Next, I have projectile square weight. I have an increase. So I look in the increase, which is column 19. So I have positive 17.0. Okay, positive, so that's going to be negative. And then over here, so that's going to be a negative times a positive. So that's going to be a negative value. Okay, so after I've extracted that, let's go ahead and do our math. So let's see here. I have 10 multiplied times 10.1 gives me 101.0. We always express this to the 10th over here. And it's the only column that's open, so I put it there. Next is 15.6 multiplied times 17.8, which gives me 277.68, which expresses to 277.7. Next I have 0.2 multiplied times 20.8, which gives me 4.18, which expresses to 4.2. And I have 1 times 17.0, which is just 17.0. Then I have 11 times 0.34, which gives me 3.74, which comes all the way over here to 3.7. All right, after I have all these values, I add up the columns. So 277.7 plus 4.2 plus 17.0 gives me 298.9. Let's add up the minus column, so that's 101.0 plus 3.7, which gives me 104.7. Okay, let's use bunk bed math. The smaller number always goes on the bottom for bunk bed math. Okay, so now that is 298.9 minus 104.7. Okay, that's going to come out to 194.2. Okay, 194.2, which then is just going to it's going to be in the positives because it's in the positive column. So positive 194.2, which then expresses to positive 194 is my met range correction. We're just going to pop that immediately down here. So that's positive 194. Now I need my delta V range correction, okay? So earlier we worked right to left of the concurrent met, but here for met plus VE, we got to work left to right. Still remembering the rule for this box, and this box is samey, diffy, meaning that these two boxes will have the same sign, and this box will have the opposite sign of these two here. Okay, so we've got our VE, which is negative 3.8, but now we need to find our change to muzzle velocity for prop temp. We know our prop temp is positive 3.2. So let's go to table echo. All right, I don't need propellant temperature in degrees Celsius because this is America. Okay, so change to muzzle velocity for prop temp for 3.2 degrees. It's not gonna be listed value, so I'm gonna have to interpolate. So I'm looking for positive 3.2 degrees. So 3.2 degrees is not a listed value, but it does fall between 3.0 on top and 4.0 on bottom. Let's make our brackets here. So that's 2, that's 1.0. So that's 2 over 1.0 equals, trying to find the range, the effect on velocity at 3.2 degrees. So let's see here. So 3.0 degrees would be negative 2.8. 4.0 degrees would be negative 2.1. I don't like working in negative numbers, so I'm going to take away these negatives, hold it up here until I'm done interpolating. Know that my little bracket on the right will always be X. My big bracket over here, I would do 2.8 minus 2.1, which gives me 0.7. Okay, so that's 0.7. Yep, okay. So now I cross multiply. So 0.7 multiplied times 2 divided by 10 is going to give me a value, x equals 0.14. Express the x, the value of the column on the right, so that comes out to 0.1. Okay, so now I apply this to where the value falls between these two values right here. So I'm going to subtract 0.1 from 2.8, so that becomes 2.7. Sanity check, does that fall between these two? Yes, it does. Let's pull down our negatives. And so that means that our change to muzzle velocity for prop temp is going to be negative 2.7 meters per second. Okay, now I just add these up. So negative 3.8 plus negative 2.7. Oop, that's not correct. So that's 3.8 plus negative 2.7. All right, it's going to give me negative 6.5. So my delta V is negative 6.5. Now that I know the sign for this, I can go ahead and get the sign for this, but I have to find these values up here. You could have found them earlier when you were getting the unit corrections in Table Fox, but we'll just go ahead and get them now, okay? So Table Fox, what would we say? This is muzzle velocity, yep, so range 8300. So a decrease in muzzle velocity at range 8300 would be positive 21.2. An increase would be negative 20.8. Okay, so now that I see that this value is negative, and using the rule diffie samey samey, right? If this is diffie, I need the samey samey. So I need a value here that is different from this one, so that's going to be positive. So positive to 1.2, and I know whatever I'm about to solve for is going to be positive over here. Okay. So let's go ahead and do that. So samey samey diffie. So that is 6.5. Times 1.2 is going to give me 138.8, which is going to express, so I'll just do positive 138.8, which will then express to 137.8. My fault. I misrecorded that. So it's 137.8, which expresses to positive 138. Okay. So now that I have that, I can go ahead and add up my met range correction and my delta V range correction, right? So that's going to be 194 plus 138 is going to give me my total range correction of positive 332, which then I express to the nearest 10, which comes out to positive 330 is my total range correction. Now that I have that, I can apply that to my lazy Z. So that is positive 330. Okay, so now that we found our total range correction, that is the second out of 3 total corrections that we need, right? Total range correction we said was positive 330, and we put that bad Larry right there, positive 330. Okay, so now that I have this, I can start my met fuse correction. So I need all these values here, but I already found the variation from standard up here, right? Let's start with my delta V. So my delta V is negative 6.5, which is assuming the standard is 0 meters per second. That is a decrease in 6.5 from standard, right? My range wind, we got this up here, was a tailwind of 10. My air temperature was a decrease in 15.6. My air density was a increase of 0.2. And my projectile square weight was a increase of 1 square. All right, I got to get my unit corrections now. My unit corrections I get from Table Juliet. So let's go ahead and turn to Table Juliet just real quick. It'll be the second to last table. Okay, I need Table Juliet, but I say that my entry argument to Juliet is fuse setting at adjusted elevation, right? So I need my fuse setting at adjusted elevation. Adjusted elevation is this right here, did hit elevation or adjusted elevation. So I need to find this first, my did hit range. So that is did hit range, that is 8330, which is my should hit range, plus my total correction of 330, gives me a did hit range of 8660. Now I need to find my adjusted elevation or my did hit elevation. So I'm going to either go into the TFT and interpolate for elevation, or I'm going to extract my GFT. I'm going to set off range 8660, and I'm going to read this right here. So that looks to be about 418 or 419, but I interpolated this earlier and discovered that it is 419 is my adjusted elevation. Okay, so that's 419. So now that I have this, I can go ahead and find my fuse setting at adjusted elevation. My fuse setting at adjusted elevation, if I look here, see here, that looks to be 29.5. 29.5 is what I'll call that. 29.5. All right, so now that I have my fuse setting adjusted elevation, I can go ahead and pop that up here. So that is 29.5, but I know I'm just gonna enter this table to the nearest whole second. So 29.5 expresses to 30 seconds. That artillery expresses to 30 seconds, okay? So now we can find our unit corrections. I'm gonna grab my straight edge so I don't accidentally extract data from the wrong range. And I got my entry range, or correction, my fuse setting adjusted elevation of 30 seconds. So that's this one right here, okay? Now, unit correction for a decrease in delta V. So a decrease in muzzle velocity looks like negative 0.045. Okay. Let's see here. A tailwind, so a tail range wind. So a tail range wind would be 0.011, so positive 0.011. Air temperature, looks like I have a decrease in air temperature, so that would be negative 0.024. Air density, I have an increase, it should be 0.2, so that'd be negative 0.027. Projectile square weight, I have an increase, so that would be negative 0.055. Okay. All right, so now that I have this, I can go ahead and determine what's going to be positive and what's going to be negative. So if this is negative, it's going to be negative. So I'm going to do my positive and negative sign here. Okay, so that's negative. So mark out the opposite. So positive, it's going to be there. Boom, boom, and boom. All right, let's multiply across. So that's 6.5 multiplied times 0.045, which gives me 0.2925, which expresses to 0.292. Then I have 10 multiplied times 0.011, which gives me 0.110. 15.6 multiplied times 0.024 gives me 0.3744, which expresses to 0.374. Then 0.2 multiplied times 0.027 gives me 0.0054, which expresses to, let me try that again, hold on. So that's 0.2 times 0.027, should be 0.0054, which then expresses to 0.005. Am I plugging that into my calculator right? 0.2 times 0.027. Yes, okay. 0.0054. All right, so let's see. And then projectile square weight right here is 1 times that is 0.055. All right, so now let's add up the columns. One on the left is super easy. There's nothing else other than this, so it's 0.110. Column on the right, 0.292 plus 0.374 plus 0.005 plus 0.055 gives me 0.726. Bunk bed math, bigger number is always on top. So 0.110, so 0.726 minus 0.110 gives me 0.616. All right, now that is my met fuse correction. So I'm gonna pop that up here and just express that to the nearest tenth, which is 0.6. Specifically, because it's in the minus column, it is a negative 0.6. So my met fuse correction plus my pause fuse correction gives me a total fuse correction of negative 0.6. And then I pop that bad Larry right up here, negative 0.6. So I just found my third and final total correction that I need. Okay, so I'm just going to highlight that. Now what I do with this is I take 29.5 minus 0.6 gives me 28.9. Right, double check the work. 29.5 minus 0.6 gives me 28.9 is my did hit time fuse setting. Okay, so now that I have this, let's go back to our homework requirement. Okay, so we completed the MET plus VE. Are there any other requirements for this one? No, but let's go ahead and let's just go ahead and draw out what our GFT setting would look like, right? It's good practice to always record your GFT setting after completing a DA Form 4200. So looking at my GFT setting notes right here, so I'm going to follow U caret, right? So U is unit. So this is GFT alpha, because we're alpha battery. C is charge. So we said this is charge 2, right? Lot, so ammunition lot, we said was alpha lima. Okay, so should hit range. So that is from here, from my lazy Z here. So should hit range is 8330, followed by elevation. E is elevation. That's my adjusted elevation of 419, followed by my did hit time of 28.9. Let's go ahead and draw our lazy Z. Okay, so total range correction of positive 330 gave us 8660 as our did hit range. Down here I have 29.5, which is my fuse setting at adjusted elevation, or my should hit time fuse setting, and my total fuse correction of negative 0.6. All right, so this is the first part of my GFT setting. But what else do I need? I also need my total deflection correction and my GFT deflection correction. So my total deflection correction that we calculated up here was left 2-1 minus drift at adjusted elevation. I want to strip out the drift. Okay, so to do that, I'm going to refer to my GFT. So elevation 419, I look up and I see that I have a drift of left 10. So total deflection correction of left 2-1 minus drift at adjusted elevation of left 10. So think of these as positive numbers, right? Left, and when I'm dealing with deflection, left is positive numbers. So that's positive 2-1 minus positive 10, which gives me 1-1, specifically positive 1-1. So that would be left 1-1. And that is my GFT deflection correction, is left 1-1. Now, just in case we need it, what we should always do anytime that we calculate a GFT setting is we need to calculate range K. If I forget how to do range K, I just put a line here and I divide this number by this number. So range K is going to equal 8660 divided by 8330. That's going to be 8660 divided by 8330. So that's going to be 1.09 or 1.0396158, which we express to the 4 beyond the decimal points. That's 1, 2, 3, 4. So it'd be 1.0396 is my range K. Okay, so requirement 2 complete. That is the completed DA form 4200 and the completed GFT setting. So let's move on to our next requirement.